Dear colleagues, I will describe the study of active faults during engineering investigations of lifeline roads. Active faults play an important role in landscape evolution, and here you can see some examples of surface ruptures produced by historical large earthquakes. Of course, such displacement can destroy almost any structure if it would affect it directly. Here you can see the dam ruptured by the 1999 Chi earthquake in Taiwan, when fault passed along the river and was missed during site investigations. Outline. First, we will start with active fault definition, which is important. Then we will talk a little bit about aims of active fault study that is used to delineate seismogenerating zones or causative faults and to assess possible displacements at structures' foundations or across lifeline roads, which will be the main goal of the lecture. Briefly, I will describe basic methods of active fault studies: remote sensing, laser scanning, field reconnaissance, trenching, geophysics, geodetic measurements. Then we will discuss peculiarities of studying active faults for different types of lifelines: highways and railways, roadbed, high voltage power lines, and oil and gas trunk pipelines. And then this will describe design parameters of active faults and accuracy of their assessment for trunk pipelines design, age and recurrence intervals of displacements, localizations, fault kinematics, and displacement value. Sorry. Active fault definition. First of all, we must define what do we mean classifying a fault as an active one. Generally, main goal of our studies is to provide designers with input data allowing either elaboration of the efficient and economically reasonable construction of the lifeline that crosses such fault, or to justify the necessity to change lifeline road. If one will just say that lifeline road is crossed by active fault, not providing any quantitative characteristics of this fault, it will be basically useless for the designer. The most commonly used definition of active fault is: fault is considered as active if it moved at least once during some given period of time. The main discussion is about the duration of this period of time. In most of the construction codes and recommendations, this value varies from about 10,000 years to up to 100,000 years. Some researchers recommend longer period, up to 1 million years or so. But such definition does not include characteristics of the displacement value or slip rate. The parameters that are used by engineers for calculations and design, they use just this period data, not duration, not age of the displacement. So we propose the following definition of active fault that is used in some Russian construction codes. The tectonic fault should be considered as active if there are evidence of permanent or periodic movements of its walls in the last about 100,000 years, with such single event displacement or permanent slip rate that poses threat to the structures and requires special constructional or layout measures to ensure its safety. I must notice that for different types of structures, different types of lifelines, these criteria, displacement or slip rate, may vary. If lifeline crosses fault that is considered as active, then special measures should be elaborated, either to protect it from adverse effects or to minimize them at least. Fault crossing design predetermine what parameters should be provided by site investigations. I must point out that processes associated with tectonic faults, but affecting the structure in other ways, like karst, erosion, various fluids passing through the fault, and so on, require other protection measures and are not analyzed hereafter. Such site or road investigations have special requirements for the accuracy of the active fault's localization and their design parameters assessment, and are based on direct evidence of fault activity mainly, rather than on indirect evidence that are often used for regional seismotectonic studies. The direct evidence are the traces of past displacements of recent landforms and/or deposits, and various geodetic data allowing measuring fault slip rate. So what are main methods of active faults identification and study? Here I will focus on identification of seismic surface ruptures mainly, that occur with significant time intervals and may not experience any movements between such rupturing episodes. First of all, these are remote sensing methods. What is very important? We must differentiate faults that really displace recent landforms and deposits from those faults that are very well expressed in landscape and on space images, but just due to glacial or water erosion or wind denudation of old geological structures. I will show you some examples. Here we can see the Upper Piltun active fault marked by arrow. Photo was made before 1995 magnitude 7.3 Neftegorsk earthquake that occurred in Sakhalin Island. Here is this fault. It is not very well visible. And now look here. It is the Kola Peninsula, northwestern Russia, with numerous ancient faults highlighted by glaciation and post-glacial erosion. They are visible much better, but generally they are inactive. One more active fault. It is Kura active fault in Azerbaijan. It passes here, and now look here in a large section where it is the fault scarp is very well visible. It displaces river terraces here. And another site. Again, here it might be not so impressive, but this site is more, let's say, perspective for detailed study by trenching. Fault passes here, and we can see that at some section in the center of the image, a river gullies, stream gullies in the hanging wall are incised much deeper than in the foot wall. This particular site is most favorable for detailed trenching investigations. It is an aerial photo of another fault, very well visible on the slope. And now let's look how it looks like in the field. Here, measured vertical offset is about 6 meters, and it occurred about 2,000 years ago. One of the most efficient methods of active fault study is the airborne laser scanning. It is the Chilmakan fault in southern Yakutia. It is its digital elevation model produced by laser scanning. And it is interesting that besides the main scarp, which is very well visible, we can see an additional rupture marked by red arrows. And how it looks like in the field from the helicopter in April, when area was slightly covered by snow. Here we can see the near fault graben up to 2 meters deep, indicating normal style of faulting west of the trunk gas pipeline marked by a blue line. We can also derive assumed components of lateral motions that are shown by yellow arrows. It is also data derived from laser scanning, which allows not only visual but quantitative characterization of fault displacements. This site, which was shown before, is interesting because the amount of transverse extension can be estimated using such model. Area of the graben should be equal to the area of fault wall separation. Deeper the point of the change of fault gradient is, smaller the extension should be. It is data from McAlpin's paleoseismology. One more example, evidence of recurrent surface faulting in Baikal Rift Zone close to rejected road of oil pipeline marked by red line. What is interesting here, we can see very clearly two traces of active faults, one of which is definitely younger than another one. Field study of active faults include geological and geomorphic reconnaissance and trenching. Here we can see the site in Pamir, where the Obihingo River goes out from the range, and we can see an active fault passing along the range foot. In these images, we can see the same active fault and how it was investigated. We could not trench it due to some reasons, but analyzing landforms displaced by this active fault, we could derive first number of rupturing events, and second, we can derive amount of single event displacement, comparing the profiles made across displaced terraces and across fault lines. Here we can see series of terraces profiles displaced by faults, and here we can see the profile across fault scarp with vertical offset of the terrace number 2 measured as 6.7 meters. Some other evidence of the recurrent surface faulting, one can be seen on this photo, again from McAlpin's paleoseismology, where we can see very clear surface rupture of the 1983 Bora Peak earthquake in Idaho, with 2 meters vertical separation, and line slope from sea to sea point is the eroded fault scarp, indicating offset of the previous earthquake. Sites for trenching should be selected during field reconnaissance. Here we can see the active fault scarp in northern Sakhalin that was selected for trenching here. And here is the photo documentation of the trench wall. And enlarged section is shown above, and its documentation and interpretation, and with sampling sites are marked out on the lower image. One more trench in Sakhalin, it demonstrates the necessity of very accurate preparation for documentation. Trench wall selected for documentation must be cleaned and marked by a rope net, usually with 1 to 1 meter spacing. Sometimes, to localize fault plane as accurately as possible, several trenches must be excavated and logged, as at this site at the Sakhalin II pipeline road. 3 deep trenches were excavated to identify exact position of the rupture plane. The best textbook on studying active fault is the second edition of the Paleoseismology, edited by James McAlpin. It was published in 2009 and translated in Russian and published in 2011. Some examples of trenching from this book. It is the County Dam Fault in Albuquerque, New Mexico. You can see several outcrops cleaned and logged. Trench across the Wasatch Fault in Utah. You can see the size of excavation here. But it might be even bigger. It is a multi-bench trench excavated by scrappers to investigate 20 centimeter wide fissure at construction site in California. Besides geological studies, geophysical methods, seismic profiles, electric tomography, georadar, are used as well. They help to localize fault plane and to study fault structure deeper than it can be excavated. Here we can see the seismic profile across the Chonaksu fault in Kyrgyzstan, ruptured last time in 1911, combined with a trench log. Trench log is on the right, and geophysics allow some data about how these fault planes can behave below the trench bottom. One more example, electric tomography profile across the Chilmakan fault in Yakutia. Profile was made along this section marked by white line. And here we can see the position of fault plane. The same profile, but ground penetrating radar data along the same profile, and again fault plane. Geodetic measurements. I will not stop on it in detail. I want just to mention that such methods, recurrent leveling and triangulation, GPS measurements, INSAR and so on, are especially efficient for study of creeping active faults with permanent slip and for monitoring of the state of the existing lifelines that cross active faults. However, the problem is that they require long-term, multi-year observations and therefore can be rarely used for site investigations performed for new projects, except maybe the retrospective analysis of the INSAR data. What is important that for the geodetic measurements we must set up the benchmark geometry in such way to be able to distinguish fault movements localized within narrow zone from overall deformations of large tectonic blocks. I will show it by example. The white line is the lifeline, red line is active fault that cross it. If we have 2 benchmarks, for example, and we found that they were displaced either in plan view or by leveling, we cannot say what is the style of deformation that forced these benchmarks to move. We need additional benchmarks, and only with such network we can say what is the style of these deformations. Either it is the overall deformation of large blocks, or it was displacement concentrated within narrow fault zone. I have to say that study of active faults, amount of work, their accuracy and so on, strongly depend on the type of lifeline. For we will describe a little bit highways, railways, their roadbed, high voltage power lines, oil and gas trunk pipelines, which will be the main focus of further lecture. When planning active fault study for site or road investigations, we must always take into account how this data can be used in the design, how active faulting can affect structure safety and environment, and what is the ratio between the site investigations cost, the design, construction, and exploitation of the remedial measures on the one hand, and of the possible losses and restoration cost in case of surface rupture. Let's talk about roads and highways. It is an example from 2008 Wenchuan earthquake in China. We see the road was displaced by active fault, but nothing terrible occurred in this particular site. One more example, 1999 Chichi earthquake. This stadium road was displaced, but it is very easy to repair it. The same, even easier maybe, is for the road in New Zealand displaced right laterally during the 2010 Darfield earthquake. It is difficult to maintain workable conditions of a road crossed by surface rupture with large displacement. In most of cases, it will be much cheaper to restore it damaged section rather than to try to prevent roadbed deformation. It seems reasonable just not to use, say, overhead road at those sections where it is crossed by active fault, because it will be much easier to repair it if displacement will occur and if there will be no bridge or overhead section. In such cases, we just need to identify active fault and to provide rough estimate of the assumed fault kinematics and displacement value to make well-grounded decision on the highway layout. No need to study this fault in very much details. Railroads, railways, especially those for high-speed trains, seems to be most sensitive for deformations produced by active faulting. But I cannot imagine construction that can accommodate ground deformation produced by strong earthquake accompanied by surface rupture in such way that rupture would not affect the railway usability. If railroad will be affected by such an earthquake, it will be inspected definitely before further use and repaired if necessary. Look on this image. It is a railroad in Armenia damaged by the 1988 Spitaka earthquake, close to surface rupture. It was not directly associated with surface faulting. Anyway, diesel locomotive operation was restored here in 5 days. It seems, however, that slow permanent fault movements with a millimeter centimeter per year rate could be even more hazardous for railways. since the exceedance of the threshold deformations of the railway could be missed in this case. Such fault crossings require regular and precise monitoring. Now let's talk about high voltage power lines. Their main difference from most of other lifelines is that they have dotted interaction with daylight surface. It is obvious that the transmission towers must be placed at a maximal possible distance from the anticipated active faults. Let's say this position of power lines is good, while this one is bad. Potential influence of fault offset on the power line workability due to change of the distance between transmission towers must be analyzed together with designers that can estimate the threshold offsets, which exceedance would be dangerous for such types of lifelines. For example, if a fault motion will occur, length of the section between transmission towers might change, and how it will affect the forces affecting the wires is, we cannot say, geologists. It must be provided by engineers. And geologists should just locate active fault and find if the assumed offset is bigger than the threshold value provided by engineers or not. I must say that most of active fault studies have been performed during engineering investigations for trunk oil and gas pipelines. Such type of lifelines can really withstand large multimeter fault offset without rupturing of the pipe and without environmental pollution. And it was demonstrated directly by Trans-Alaska Pipeline that survived about 6-meter offset during the 2002 Denali Fault earthquake. It is this section. It was directly designed to withstand 6-meter offset, and just same displacement took place at this fault section during the 2002 earthquake. Here was the Denali Fault rupture, and we can see how this section of on-land pipeline was designed. Here is the limit, some boundary pipeline strike this static of pillar. Active fault parameters used for the design of trunk pipelines are: first, active fault location, where it is; fault kinematics, ratio between displacement components, and I must add that another important parameter is orientation of active fault relative to pipeline road; design displacement, net and component wise. And for a risk assessment, not for the design, it is also important to know the recurrence interval of surface faulting and the age of the latest event. It allows estimating the probability of such event occurrence during pipeline lifetime, which is about 30 years according, for example, Russian construction code. These data allow to make a decision on should we do anything, or we can just accept the risk. Here is the idealized scenarios of the successive rupturing events along the particular fault, and it will explain why we considered past events during very long time period, about 100,000 years, for example. Here we can see the first variant. First of all, surface faulting is always studied from the present towards the past. Thus, if we will identify, for example, 3 successive rupturing events during last 3,000 years with around 1,000 years recurrent interval, we can stop. We do not need to go further in the past. We can say that there is a high probability that next rupturing event will occur within pipeline lifetime, and this must be considered. Another variant, another scenario. The same age of the last event, about 1,000 years ago, but recurrence interval is of the order of 15-20,000 years. It means that if it will continue, future event will occur somewhere in the long future. In this case, probably, despite recent age of the last rupturing event, we can accept this risk. But there might be another, third variant. For example, we know that in California, faults are considered as active if rupturing event occurred there within 11,000 years. In this case, the last event occurred earlier, around 12,000 years. Fault might be considered as inactive. But with 13,000 years recurrent interval, it appeared that the next event again might occur within the pipeline lifetime. That is why we need to study in such cases the history of rupturing of events for a rather long time in the past. Now, position of the anticipated fault plane. I must say that it always can be defined with some scatter. Here is an example of a strike-slip fault in California, again from McAlpin's paleoseismology, where rupturing planes occurred within a narrow zone of about 4 or 5 meters. Here, it is a reverse fault at northern Sakhalin, and again, rupturing events occurred along some fault planes within, say, 10-meter wide zone. Then, besides main fault plane, sometimes there is a significant zone of so-called secondary deformations, most often within the active block. And here we can see the tension fractures in the hanging wall of the reverse fault that was ruptured last time by the 1911 Kimin earthquake in Kyrgyzstan. Here is the main fault plane, and here we can see how these fracture tension fissures looks like. Highlighted is the person staying in such a fissure. Finally, we came to the decision that besides central line of active fault shown, let's say, on the map, we must always define some uncertainty zone with the probability of faulting within this uncertainty zone that is considered to be equal within its entire width. I must point out that in Alaska case, in Trans-Alaska Pipeline case, a rupturing event occurred very close to the lateral edge of the assumed fault zone, not in its central line. Fault kinematics. It is assessed by field reconnaissance and by trenching. We can define normal faults characterized by extension and vertical separation, reverse faults or thrust faults, again with vertical separation but with compression. There are strike-slip faults, and of course there is often a combination of different kinematic types. The most difficult task is to provide the correct and well-grounded estimate of the design displacement value. I want to say that the design based on larger displacements provides higher safety level, but at the same time makes the construction of the pipeline and at fault crossing more complicated and expensive, and we should find some balance between risk and economy. The problem is that seismic surface offsets are characterized by significant variability, both for the given earthquake magnitude and rupture length, along fault strike. Besides, the successive events might produce different offsets at a particular point as well. Here we can see plots demonstrating relationships between maximal displacement. Each point shows the maximal displacement during the particular earthquake included in the analysis. And on the left, earthquake magnitude, and on surface rupture on the right. The possible scatter of maximal displacement is about 2 orders for the given earthquake magnitude and for surface rupture length. Using such plots, we can estimate quite reasonable either average maximal displacement or, using the envelope, maximal possible displacement, which will almost always be quite large. Here we can see displacement variability along the strike of the historical surface ruptures. And you can see that they are quite different. There are faults with maximal offset in the central part of rupture, at the edge of the rupture, at one end of it, and there are multi-horn, ruptures with several maximal sections. Maximal single event displacement at largest earthquakes can reach 10-15 meters, but they are typical usually for a small part of the entire length, usually for less than 5% of their entire length. Another important characteristic of surface rupture is its weighted average offset, the average. And here you can see the plot demonstrating how to calculate it. In this case, maximal displacement is characterized for D4 section. Another important parameter is the length of surface rupture section characterized by maximal displacement. And a red arrow show how to calculate this particular value. Why not to use this value? The problem is that weighted average offset can be really typical of the large portion of surface rupture as it is shown at picture A. But can be quite rare as well. That is shown on picture B. At A, it really is typical of a long section of this fault, Nevada earthquake fault of 1954. But in the lower plot, you can see that longer sections are characterized by small and by large offsets, while average value is typical of a very small section and might be found just accessionally. Thus, average displacement cannot be recommended as a design displacement value, at least without special analysis in each particular case. Another interesting example, slip variability along the Chilmakan active fault. I showed it already. The problem was that this fault was crossed by two pipeline roads. One crossed it at the section where cumulative offset of two successive events was minimal, another where it was close to maximal. What value should we recommend for the design? Should it be different or should it be equal? Will the this slip distribution be the same for the anticipated future event or not, or it will be opposite to say how somehow average long-term deformation along this fault? We do not have clear answer on this question. To protect buried pipelines that have to cross active faults, special trench and special seismic class pipe are used. Here you can see it. Significant efforts, for example, were undertaken during site investigations and construction of 24-inch oil and 24-inch gas buried pipelines of Sakhalin-1 and Sakhalin-2 projects. At this particular site shown in the picture, the design displacement was set up as 4.5 meters with a reverse fault kinematics. Fault line crosses the pipeline road quite far at the background, and you can see how complex was the crossing site design. One more problem. Tectonic creep, permanent slip rate. Some faults really demonstrate permanent creep, and its measurement is possible based on the precise repeated geodetic measurements only. Generally, displacements with a slip rate of the order of millimeter per year should not pose a significant threat for the trunk pipelines with the, say, 30 years operational lifetime, since cumulative offset during this period will not exceed several centimeters. It should not be dangerous for the steel pipeline. But the problem is that if evidence of recent movements does not allow to define strictly, are the fault movements slow permanent, or they are associated with earthquakes, it is better to select more conservative approach and to consider that offset at that particular site could be a single event, seismic rupture. The slip rate is an important parameter used for seismic hazard assessment, and it characterizes generally an average long-term rate of fault motions. It should be pointed out that it might be the real permanent rate, but in most of cases, just a mean value averaged for a millennia-long time intervals. So, if calculated slip rate is 1 millimeter per year, it may correspond to real every year millimeter of set, to 1 meter of set once in 1,000 years. That corresponds more or less to the magnitude 7 earthquake. It might be 5 meter of set once in 5,000 years. That corresponds to a much larger earthquake with magnitudes of, say, 7.5 or 8. So, if paleoseismological studies provided that the study fault had ruptured every, say, 1,000, 1,500 years with 2-meter displacement, which is considered as ductile level value for the design, it doesn't mean that the strength level value, which is considered as for the design as the event that might occur once in 200 years on average, will be smaller, will be 30-40 centimeters. No. If displacement will occur, it will be of 2 meters, and just this value must be considered by the designers. The accuracy of the design displacement estimate depends on numerous factors, and scatter, as it was shown above, can be quite significant. That is why it is necessary to investigate pipeline stress-strain state sensitivity to displacement and kinematic variations. Geologists studying active faults must work in close cooperation with pipeline engineers from the beginning of the project. It was found that safety of pipelines crossed by active faults with relatively small anticipated displacements can be ensured even without applying expensive measures recommended by construction codes that can cut down pipeline construction cost. These, let's say, small values depend on pipe diameter, trench shape, and backfill, and should be estimated for each pipeline fault crossing individually. However, the chance to use normal pipe in ordinary trench for such fault crossings should cover all additional investigation and design costs. Here is an example of maximal longitudinal strains in the pipeline caused by active fault with different kinematics and with different backfill. Beta is a trench slope angle. And such analysis should be very useful for planning of the engineering geological investigations at the pipeline fault crossing sites. Main focus should be paid on getting more detailed information on those parameters that influence the resultant strain in the pipe at most, and on understanding if the assumed offset or fault kinematics will exceed the critical value with which strain will become inaccessible or it will remain acceptable. Thank you for your attention.